So we're discussing this system in terms of checking the linearity and the time variance. And we found that if you consider Vn1 as the input and V out, while you consider Vn2 something internal to the system, you end up with a non-linear but time-varying system. If you go and consider Vn1 as internal while Vn2 is the input to the system, the same output is measured, then the relation becomes linear, but the system also, in that case, stays as time-varying. Now, the next thing was to show you that, so I'll skip those two slides, because they were just trying to calculate the output for certain inputs. The idea of this slide is to show you that even for a linear system, but if it is time varying, you can actually produce other frequencies at the output that are different from the input frequency. Why does this matter to us? First of all, remember that for a linear time invariant system, so if your system is linear and time invariant, then for that system, if you put some input, let's say a single cosine, so cosine omega 1t, what you will get at the output is going to be definitely the same frequency, so omega 1t, but you might have some phase shift and some amplitude factor, right? If the system is linear time invariant, no matter what you do, if you put an input which is a single cosine, you will get at the output the exact same cosine at the same frequency, but it might experience some phase shift and some amplitude variation, okay? But you are not going to get any other frequency at the output. For a linear system, but time varying, you can actually produce output frequencies that are different from the input frequency. Why does this matter? Because this is how we do modulation. This is how we do the operation of what we call a mixer. We multiply an input signal with some cosine, and we end up at the output of a mix of the two frequencies that allows us to control the frequency of the output, right? Now the example here shows you that if you choose Vn1, which is something internal to the system design, right? If you choose Vn1 to be a square function, the one that we see here, remember that Vn1 is performing switching on and off, right? So if Vn1 is 0, then the output is going to be a 0 voltage, right? And if Vn1 is 1, is switched on, so the switch is connected, the output is going to be exactly the same as the input, right? Now if you think of that, this means that you can represent the output of this system as the multiplication of whatever input signal you put with that square function, right? Correct? Okay. If this is the case, does this multiplication allow us really to do what I claim that we can do? We see that from your signals and systems background, and again, I'm not asking you really to do that mathematical analysis yourself in this course, no, but just the concepts themselves, and I will explain how this happens quickly here, right? We agreed already together that the output is going to be simple time domain multiplication of the input signal with something internal to the system, which is this S of t, which is this square function, right? Okay. Now, if you want to look at what happens in terms of frequency components, the best way to do that is to look at everything from the frequency domain perspective. Now, if you go to the frequency domain, this relation, which is multiplication in time, becomes convolution in frequency. The first signal, which is Vn1, the input to this system, right? You just need to take its Fourier transform. An arbitrary signal would look in time domain this way. When you take a frequency frequency domain representation or the Fourier, it looks this way. Just some signal that has this frequency domain look and this time domain look, okay? The important thing is to notice that in frequency domain it's confined to a band that we see here around 0, okay? Now, when the convolution here happens, you need also to get the frequency domain representation of this square function. The square function is a periodic function, and each period has a square, right? You know from your signals and systems that this will look, regardless of the values of the amplitudes and everything, this will look like the Fourier of the square multiplied by impulses, train of impulses, and those train of impulses exist from minus infinity to infinity. Okay? So this is what it looks like. The sink, which is the Fourier transform of the square, and then multiplied by the train of impulses at different frequencies, right? At f, and at f minus 1 over t1, f minus 1 over t2, f plus 1 over t1, f plus 1 over t2, and so on, right? So a train of impulses as we see them here, okay? When you do the convolution of something with deltas at shifted points, you get the same thing placed in the locations of the deltas, right? Whether in time domain or in frequency domain. If you do this convolution, the result is going to look like this, with certain scaling factors, of course, of the signal depending on the amplitudes of the deltas, okay? So we ended up with what? The output of this signal is no longer around 0. It has frequency components around f1, 3f1, 5f1, minus f1, minus 3f1, minus 5f1, and so on, right? So now this system is linear, but because it's time varying, I was able to produce output frequencies that did not exist in the input, right? If it was linear and time invariant, I would not have been ever able to do this, okay? Remember that I was able to do this by designing the system itself to do the operation, right? Okay, that's when I selected this to be my VN1, okay? Any questions? That's how we get mixers to operate, okay? So in mixers, we simply have some multiplicative factor here, which is the cosine function. We have our input signal, which is whatever desired signal that we need to modulate, and the output is going to be the multiplication of those two, which is basically shifting in frequency. When you look at it, you will see that the signal has been shifted in frequency. Okay? Fine. Now we go to other effects. So now we talked about time invariance and time varying systems. We also discussed linear systems. Now we will discuss what if a system is nonlinear. What's bad about that, and what's good? What can I use it for? Okay? Before going into that, I just remind you of an important concept, which is the concept of memory in systems. A system is memoryless, which means that the output at any point in time depends only at the input at the same time. So the output at time t does not depend on what was the output at t minus 1 or t minus 2, or t plus 1, t plus 2, t plus... It only depends at the input at time t. And if the system is linear, then this is generally how the relation would look like. Y of t is equal to some constant multiplied, but maybe with an added constant as well, plus alpha 2 or plus alpha 0 or whatever, okay? But generally speaking, it's going to look like the output at time t is dependent on the input only at time t. In general, and I hope you still remember that from your signals and systems course, in general, most of the systems that we deal with, even the linear time invariant systems, most of them are with memory, right? The only exceptional case is if the impulse response was a single delta. That's the only case where the output of the system is going to be dependent only on the current input of the system. For any general h of t, remember the convolution operation. You take one of them, you shift it, you move the other over it, so you end up depending on the input at many times. The output at any point in time depends on the current input, previous, and so on, right? And if it's causal or non-causal, it will be dependent also in future, right? So generally speaking, most of the systems that we deal with, they have some memory to them, except the only exceptional case, which is almost practically impossible to produce, is the delta function impulse response, right? So we have to keep in mind that whenever we deal with systems, the current input, right, and some of the previous inputs are having some effect on the output that we see, okay? Now let's go again, when we look at things, let's look at the ideal situation. So let's consider only memoryless systems. And the difference is going to be that you will have some more terms here that are t minus tau, t minus 2 tau, t minus 3 tau, and so on, right? But it doesn't matter at this stage. A system is linear, as I mentioned a little bit earlier, if the input-output relation is a linear function of the input, right? So the y of t is equal to x of t multiplied by some constant. We are considering here memoryless systems, to forget about the memory effect now, okay? And if the system is non-linear, this means that the output not only depends on the first order of the input, but it has higher orders of the input as well. The output is no longer a linear function of the input. It becomes a non-linear function. The general way we express this is by using the polynomial representation. Why?
It's general.
It is a general case. Why it's a general case?
Usually
Math, which one? Calculus 2. Calculus 2. Why? Yeah, because any function, you can express it as a polynomial expansion, for example, using Taylor expansion, right? So if it was actually that y of t is equal to cosine x of t, right? That's a nonlinear relation, because the cosine is nonlinear. I can express this as a Taylor expansion. So I can say that y of t is equal to constant 1 plus constant 2 multiplied by x of t plus constant 3 multiplied by x of t squared, and so on, which is the Taylor expansion of the cosine. If it was y equal to the exponential to the power of x of t, so the output is exponential function of the input, again, you can represent that as a polynomial. So the reason we choose this representation, because it's a general way to represent things. Am I going to ask you to expand functions as Taylor series? No. But just to keep in mind why we use this relation. تمام? طيب. In general, most of the practical systems that we will deal with will stop here. What do we mean by stop here? We mean that the extra terms, even though theoretically they exist, practically they have very small constants such that we can forget them. So when we go through this course and we talk about nonlinearity, we will reach a maximum of a third order nonlinearity. We are not going to go for fourth, fifth, sixth, and so on. خلاص? So when you talk about a linear system, it means it has only a first order relation. Y of t is equal to alpha multiplied by x of t. When we talk about a nonlinear system, maximum it's going to be up to x to the power 3. And we'll stop there. خلاص? Sometimes when we talk about third order nonlinearity, we ignore the second order. There are some practical reasons for this, and we'll see those in the next couple of examples. تمام? But generally speaking, it might contain up to here. So all these terms up to x to the power q. Also, in practical cases, we try as much as possible to avoid the DC components in those nonlinear systems. Because the problem with the DC components is that they shift everything, so they can affect the dynamic range of your amplifiers and the operation of your system. Plus, they are a waste of energy, right? So you're just consuming power, doing nothing. There's no signal. It's just a DC, which is a power consumption for nothing. So we always try to avoid the DC components as much as possible. Okay. Anyways, let's look at an example of, and here you can put the hat of electronics courses, right? Let's look at an example of a nonlinear system. This is a MOSFET transistor, right? Remember that for a MOSFET transistor, we have 3 terminals. We have the drain, we have the source, and we have the gate, right? And MOSFET transistor has 3 operating modes. It can be in the cutoff mode, right? Which means that V gate is much less than the threshold, V threshold. So it's basically a switched off, an open switch. And then there is the linear region, and then there is the saturation region. Most of that, and all of that is dependent on Vn, but when you move between linear and saturation, you also consider what's the drain voltage, right? In comparison to the other quantities. So anyways, most of the time when we use this for amplification, we want to be in the saturation region. Amplification is better done when you are in the saturation region of the MOSFET transistor. In that region, the saturation region, there is a particular relation that allows you to calculate the current going into the drain. Why do I need to be able to calculate the current going into the drain in this circuit? Because the general relation between the input and the output in this circuit is what? The output is equal to the DC voltage here, VDD, subtracted from it the voltage drop across the resistor. And what's the voltage drop across the resistor? It's the current going into the drain multiplied by the resistance, right? So this is a general relation. And then I can solve this relation if I can find IDD. Solving it means what? I want to find the output as a function of the input. Tamam? In the saturation region, the IDD, or the ID, sorry, is given by this expression that you see here, half mu n multiplied by the oxide capacitance multiplied by W, the width of the channel, divided by L, the length of the channel, and then the input voltage or the gate voltage subtracted from the threshold, the switch on, switch off threshold, and this quantity is squared. And this is the ID. When we are in the saturation region, not in general. This is the case of the saturation region. Now notice that, again, all of this is going to be given to you. So I'm not going to ask you to analyze transistors again in this course, okay? But just to remind you where this came from. It's not just popping up out of nowhere, okay? All of this is just to show you that in this simple building block that we will use a lot in this course, the input-output relation is non-linear, whether I like it or not, right? The relation between the output voltage and the input voltage is a non-linear relation in general, right? I can consider certain cases with very small value of input voltage where I can approximate this to a linear relation, which is the small signal analysis. But if I'm using this for power amplifier, for example, no longer small signal. I want really my signal to be large, right? So I cannot just do a small signal analysis in that case. And I have to deal with the nonlinearity of this system one way or the other, okay? Question for you. This system is nonlinear of order? Second order, because the maximum that the input is going to go in terms of power is up to Vn squared, right? There is no Vn to the power 3. خلاص؟ طيب. Any questions so far؟ ولا الحياة سعيدة؟ الحياة سعيدة. الحمد لله. Now, here is another example. Very nice, because again, this is a very important building block that we will deal with a lot. And it's called the differential MOS, okay, block. The nice thing about this is that when you look at the input-output relation, it doesn't have any DC terms, right? And you always deal with voltage differences, whether it's the voltage differences between the gates of the two transistors, or your output is the voltage difference between the drains of the two transistors, right? If you do the analysis, and you can do the analysis, if you remember your electronics, or you start from the equation that we saw in the previous slide, if you do the analysis and try to figure out the input and the output relation for this, you will end up with a relation which is given actually in the question up there. So the output is equal to minus half mu n C oxide W over L Vn, and then multiplied by the root of 4 ISS divided by mu n C oxide W over L minus Vn squared multiplied by Rd. ISS is just a current, a constant current that you put here, biasing current for this circuit, okay? Using some current source. And current source can be done also by CMOS, just to remind you, by the MOSFET. You just connect the drain to the gate, right? So the feedback connection between the drain and the gate allows you to actually produce a current source, if I remember correctly. There's some feedback link. Okay, anyways, so that's a current source that we put, and the parameter here controls actually the response of this circuit, but that's out of the scope of what we want to do. The important part here is, now this is a nonlinear relation, but we really need to work with a polynomial expansion. And typically we stop, for example, at the third order, right? So how can we express this as a polynomial using Taylor series expansion or whatever? Simple here, if you assume that the input Vn is small compared to this term, okay? So if you assume that this term is much smaller than this term, you can actually, in that case, approximate. So the root of 1 minus x can be approximately written as 1 minus x over 2. Okay? Only if x is much smaller than 1. Right? So the same thing, if you assume that this term is much smaller than this term, then you can represent the output using this simple expansion. Okay? So under this assumption, what's going to be the output? I'm not going to ask you to do the derivation. I'm going to show you the answer. So under this assumption, when Vn squared is much smaller, because the term inside the square root was Vn squared, not just Vn. So when Vn squared is much smaller than this, you can actually use this expansion, and the result of that is going to be that V output is equal to this expression as a function of Vn. If you want to clean this and get the expression in terms of the different powers of Vn, you will end up with some constant, which is negative, multiplied by the input of power 1, some constant, which is positive, multiplied by V input to the power 3. Nice thing to notice here, we don't have a DC term. We don't have a second order term. We only have first order and second and third order, right? But the general nonlinearity here is of third order under this approximation, okay? The second thing to notice, which is very interesting because it will have an effect that we will look at later on, is that the term here is a negative term, and the term here is a positive term. The result of that is that you have an input-output relation that you see up there between the input of this circuit and the output of this circuit, which shows some linearity here, and then it starts being nonlinear, and then after it starts being nonlinear, it becomes kind of saturating. This saturation causes an effect in amplifiers that we call compression, right? If your input signal is with high value, so for example, it starts from here, and it goes up and down, right? And then you want to see with this input-output relation how it would look like in the output. Now what do you do with using an input-output relation? You project and then you project in the other direction, right? Now if you take this signal and you project it here, and then you project in the other direction, you will find that at the output, it really varies over a very small range, right? So it's gonna be something like this. So rather than amplifying, you ended up compressing the signal because the amplifier is no longer functioning. It's kind of, this is different from the MOSFET saturation. It's going into amplification saturation, but to differentiate that, we call it the compression region. So your amplifier has went into the compression region. Why? Because this term started to dominate at that point, and because it's a negative term, it's going to take out a good amount of the positive term, and then eventually you end up with very small output coming out of this circuit. We call that the compression. Tamam? We will look at it in a couple of slides. But before looking at that, let's just consider this as a nonlinear relation between the output and the input, and we know that it's of third order nonlinearity. Okay? Now let's look at this kind of nonlinearity, which stops at the third order. We said we will stop at the third order, which can be represented generally using this expression. So alpha 1 x of t, alpha 2 square of x of t, alpha 3 the cubic of x of t. If the input to this nonlinear system was a single cosine function with a certain amplitude and a certain frequency, what's going to be the output from this system? So I have a system that has this response as an input-output relation. If I put a single cosine, what's going to be the output? Cosine, cosine squared, cosine cubed, right? And then which frequencies are going to appear in this case? Remember that, exactly. You will have what we call the harmonics. So you put to the input of this system a cosine at single frequency, omega 1. You get at the output omega 1, with 2 omega 1, with 3 omega 1. Because it's a third order, we will have up to the third harmonic, right? You studied already in many other courses the harmonics, right? Maybe electronics, power systems, right? So you studied them in many cases, right? Now, these harmonics are some type good if you want to use them for your application. Most of the time they are bad, especially in communication system, because it means that I assume that I'm operating in this frequency, but because of the nonlinearity, I have actually other components in other higher frequencies, which might affect the operating band of some other user or some other entity even. And we'll see a couple of examples that shows how this happens. Anyways, in terms of convention, we call this the DC term, which does not have any cosine. We call this one, which is at the same frequency, our input, the fundamental frequency, and the other ones at double that fundamental and triple that fundamental, we call them the second and the third harmonics. Plus, tamam? Just in terms of naming. And the ones that are odd, we call them the odd harmonics. The ones that are even in terms of multiple of frequency, we call them the even harmonics. Just in terms of naming, عشان نبقى على نفس اللاين يعني. طيب, here is an example. Consider this mixer where you have x1 and x2. x1 is a1 cosine omega 1t, x2 is a2 cosine omega 2t. So you have two cosines going into this mixer. The mixer is simply multiplying the two signals together. So the output is equal to a constant multiplied by the first input multiplied by the second input. Okay, that's in the ideal case. So this is the ideal case of the mixer. Now, if some of those inputs is going through non-ideal circuitry, they might have some non-linearity to them. So we want you to solve this example in terms of figuring out. I don't want you to figure out the exact values of the amplitudes, but I want you to figure out what kind of frequencies are going to appear in the output of this system, given that the input to the system is cosine A1 cosine omega 1t and A2 cosine omega 2t. Tamam? A couple of notes. You need to solve this for the ideal case, which means the output is simply the multiplication of both, and you need to solve it for the case where x2 is suffering from a third order nonlinearity. And here it's assuming that you are dealing with first order and third order. There's no second order, there's no DC term. خلاص? Generally speaking, when I put questions, I will make them clearer than this. Because when it says third order, the typical is to assume that you have x to the power 3, you have x to the power 2, you have x to the power 1, you have a constant, right? This way, the question is kind of vague, but because the example in the book relies on some information before the example, so it was written kind of quickly, right? But here, to solve this, just assume that the nonlinearity happening to x2 is only third order and first order. So you only have x of t, x2 of t, and you have x to the power 3, x2 to the power 3. That's it. You don't have DC, you don't have x 2 to the power 2. خلاص? Now try, again, don't need to calculate the amplitudes. I want you to just try to think mentally what are the frequencies that will appear in both cases, ideal case or non-ideal case. خلاص؟ يلا. ما تقولش الحل. think واكتب بس. I need to remind you with some trigonometry. So remember that cosine omega 1t multiplied by cosine omega 2t can be represented as some factor cosine omega 1 plus omega 2 and plus or minus some other factor multiplied by cosine omega 1 minus omega 2t. Tamam? That's one thing. The other thing is a cosine of omega t squared is equal to half minus half cosine double the frequency, right? Square a cosine function, you can just represent that as cosine double the frequency, and some DC term appears as well. So taking those into consideration, should be able to solve for both and tell me which frequency components will appear. The first case is going to be straightforward application of the equation, right? So the first case, اللي هي ideal mixer, what components will appear at the output?
Omega 1 plus omega 2.
Yes.
Omega 1 minus omega 2.
Exactly. The second case بقى يلا احسب بقى. Remember, the second case will have x and will have x cube. تمام؟ No, only x2. x1 stays as is. Anyone figured out the components?
Omega 1 plus omega 2 into omega 1 plus 3 omega 2.
اوكي من غير ماينسز ولا في ماينسز كمان؟ ايه اللي طلع عندك؟ كم ترم؟ 4 اوميجا 1
4 it should be 4
4 ترمز ايه هم؟
omega 1 plus omega 2 omega 1 minus omega 2 with 3 omega 1 minus omega 2 with
3 اوميجا 1 ولا 3 اوميجا 2 اصلا؟
Omega 1 plus 3
اوميجا 2 هي اللي فيها so اوميجا yes okay so you'll have components at the plus and minus of omega 1 مع omega 2 right so these are two terms and then you will have also sign omega 1 plus or minus 3 omega 2 صح؟ This is the second case. Okay. Let's look at the answer is written in details in the next slide. في slide فاضية كده معرفش جت منين. So we have the four terms that many of you have mentioned already. The plus and the minus of the two fundamental frequencies, and then the plus and the minus of the first fundamental and the third harmonic of the second signal. تمام؟ Okay. طيب. Another example which is more practical. It's kind of a thought example, not really too much calculation.
why are we having only harmonics at omega of omega 2? Why not the harmonics of omega 1?
Because omega 1 does not have nonlinearity. Omega 1 was in without any nonlinearity. It says that the second input suffers of nonlinearity. So we only consider squaring this one. We only consider this one. اللي هو الترم ده يعني. But the first input is as is. And that's why we end up with only first يعني fundamental of that one, but the other one we have fundamental and harmonics. Okay. ده بس because the example says so. If the whole system was nonlinear, it means both will suffer from nonlinearity and then we'll end up with harmonics of everyone. Here is another example, just tries to show you a practical aspect of this harmonics. The transmitter in a 900 megahertz GSM, the GSM is like the old phone system compared to what you are using now. And it used to have two frequencies for operation, 900 and 1.8. So 900 and the double of 900. Both of them are bands used for GSM. Some users and some base stations are operating on this, some on that. And the switching between them happens automatically depending on what are the available channels for each user, which base station you are connected to, and so on. المهم إنه في الآخر عنده two bands. These two bands are operating for the whole system. تمام? Now assume that you have what says here is assume that you have a cell phone which is delivering 1 watt of power to the antenna, and again the 1 watt here was not really relevant, but trying to put some values into the example, and then it says discuss the effect of the harmonics for that cell phone. Now cell phone is now connected to the 900. Right? The harmonics of that are going to appear at double, which is 1.8, triple 2.7, 4 times 3.6, and so on. If you go for much higher order harmonics. تمام? Out of, if you say, for example, we stop at the third harmonic, so forget about those ones. This is the fundamental, first harmonic, second harmonic, third harmonic. Stop here. Tamam? Now, if this is, sorry, the second harmonic, the third harmonic, stop here. صح? That's harmonic. So we only stop here. So if we look at those two harmonics, as a GSM user, I don't really care about the 2.7 because it's outside the band, right? But I care a lot about the 1.8 because if I have large signal in that domain, I'm going to interfere with other users who are allocated to the 1.8 gig اللي هو ال 1800 or 1800 mega يعني. تمام؟ Okay. But again, if we consider now beyond the third harmonic, I can even affect other systems sometime, right? So the fundamental, second, third, fourth, fifth, sixth. The sixth harmonic here, right, is actually interfering with the Wi-Fi. So again, if I am a manufacturer of that cell phone, I have to make sure that it does not affect my system, and also it does not affect other systems. It does not affect my system because the main user of the cell phone, the carrier, is not going to allow me to put that into their network because it's affecting other users. But there is also certification entities that deals with different frequencies allocated to different technologies. So FCC, CRA here in Qatar, and so on, right? If you bring them a device that causes harmonics to other technology, they will tell you forget it, right? It cannot be certified, you cannot operate that device. Okay? So again, from a design perspective, you really care about the harmonics, and the idea is that you cannot eliminate them, but you want to make them very low, such that they are negligible for the main user. If they happen, they don't affect the performance of that main user a lot. تمام? It's a very simple example. Going back to this example, and I told you that we'll come back to this part later. Going back to this example of the differential circuit that we looked at earlier, and we found that it has first order and a third order with two different signs here. Right? Those kind of circuits, or those kinds of nonlinear circuits, we call them compressive. Because at some point, the input-output relation is going to saturate. The output coming out of this system for your input is going to drop rather than continuously increasing, right? If the two terms are with the same sign, both positive or both negative, typically they become both positive, typically. Sometimes the circuit flips as well, the polarity, okay? But anyways, if they have the same sign, then we call that an expansive circuit. Most of our circuits are of differential type, and most of them are compressive. So they have a certain operating range, which is nice to operate in, and then outside that range, they become very compressive. The compression increases, and then we consider the circuit no longer operating. It's no longer an amplifier. It's no longer a filter. Things becomes really not working as they should be. Tamam? We have to define, from practicality, we have to define a point at which we say beyond this, we cannot really use this element for the function that we want. That point is called the 1 dB compression point. So if this is the input-output relation in terms of voltages, where A is the amplitude of the input, and An is the amplitude of the input, and the out is the amplitude of the output, and the input-output relation looks like this. If the relation was ideal, it should have been a line, right? Linear, and does not saturate at any point. Because of the nonlinearity and the saturation effect, the relation deviates from the straight line. We define the point at which the deviation of the output, the actual output, from the desired ideal output, where this difference reaches 1 dB, we call this point here the 1 dB compression point. Okay, so your amplifier, for example, comes with some specs. You will typically, in your power amplifier or even low noise amplifier, you have a specs that talks about the gain or the amplitude of the harmonics. So this is the amplitude of the second harmonic, third harmonic. And they also give you something called the 1 dB compression point. So if your input increases beyond a certain value, typically in volts, for example, then your output is going to saturate. So at that point, saturation reaches 1 dB. That's the point where after that you cannot put an input to this amplifier and assume that it will work as desired. Okay. Now you can do some calculations, assuming that we are dealing with the previous. So we are dealing with the general relation, the input-output relation, up to the third level, and we are dealing with an input which is an A cosine omega t. That's my input. Then if you try to deduce the relations with the sinusoid, third order nonlinearity, we did this example much earlier, right? So for that case, we can deduce the output, input-output relation, or the output for the cosine, right? And then from that one, we try to look at what we are concerned with is what's happening at our fundamental frequency, right? In terms of the compression. So we assume somehow that we can filter out the harmonics. That's a different effect. Now we want to see what's going to happen to the output signal amplitude as we increase the input signal amplitude. The input signal amplitude is A, which is what we call AN, and the output signal amplitude is going to be whatever is multiplied by the cosine at the output, right? And then when you put that relation, so whatever is multiplied by the cosine here is the alpha 1A, and then the 3 alpha 3A cubed over 4, right, this part. This is the output, because this is coming out of the circuit, out of the nonlinearity of the circuit, right? Okay? And then you have to equal this with what would have been the output if the system was linear. What's the output of the system was linear? It's going to be alpha 1 multiplied by cosine. So it's just alpha 1, right? So if the system was linear, the ideal system there, it would have been only alpha 1, right? Now we are dealing with a dB scale, so you take 20 log that dB scale for amplitudes. That's why it's 20 log. You take 20 log of that one, and then you want to get the drop of 1 dB, so you subtract from the ideal one the 1 dB. You equate this with the other side, and this will tell you the relation between alpha 1 and alpha 3 at the point of the 1 dB compression point. So basically, if you know alpha 1 and alpha 3, you can actually calculate what's the maximum input after which you pass the point of 1 dB drop. خلاص؟ واضحة يس.
وين راحت ال A اللي كانت مضروبة في الألفا 1؟
أنهي إيه؟
There is an A that will take common factor.
This one؟
آه.
ما هي دي اللي بنسميها ايه ان. Which one?
يعني في we took the we took like a common factor A. So an A common factor.
A common factor.
Because it's alpha 1 A plus 3 alpha 3 A power 3. Then we took an A common factor for this.
A common factor. لا هو an A is existing here as well. That's why it cancels from both sides. Yeah. لأن هنا في عندك alpha 1A لو كان if the system was ideal, right? So you have A here and A here. So it cancels from both sides. مظبوط؟ So احنا we are trying to equate the ideal case minus 1 dB with the actual case. تمام؟
Should be there is so that
Yeah. So A is taken from both sides. Yeah. Okay. تمام؟ Any other questions? So basically, the whole idea here is, if I know the polynomial factors, the first one and the third one, I can easily find out what's the amplifier 1 dB compression point. تمام? Yes.
شلنا ال 1 dB هيبقى find the maximum input that we have a linear relationship.
لا، لو شلت ال 1 dB كأنك انت مكمل كده. يعني مش عارف لو شلت ال 1 dB هتبقى بتفايند ايه؟ يعني قصدك without this I don't think you will be finding anything.
we will find like that where it's like still like almost the same.
Yeah. Where is zero?
Where the difference between them is zero.
The difference
They are
between
equal. They are
something
both
like
equal.
this مثلا.
So here, yeah.
Maybe. I didn't really think thoroughly about it. Maybe you are right. Remove the 1 dB.
So we're equating this term when it's like ideal. How long is it ideal?
I need to think about it. يعني you are saying that I'm dealing with this is the first order only. So this is included in harmonics. Yeah, maybe I'm trying to find the point where they start deviating from each other. Maybe you're right. Yeah. The point where the non-linear is going to deviate from the linear. Maybe. Yeah. Looks like so. Okay. Good question. Any other questions? أول مرة أعرف إن أنا ممكن أعمل 2 pointers. That's very interesting. Never thought of this before. And I don't know what's the use of doing 2 pointers. يعني. So this is kind of a practical discussion. Gain compression, how does it affect AM signals versus FM signals? Signals where the information is in the frequency versus signals where information is included in the amplitude. تمام? Assume you have amplitude modulated signal, so the information actually of your transmitted signal lies on the envelope of this signal, right? That's for the AM. Okay. And on the other part, you have an FM, a frequency modulated signal, so the information actually is contained in the frequencies. تمام؟ هنا frequency مختلف, هنا frequency مختلف, and so on. So it's included in variations of frequency. تمام؟ If you take both of them through a compressive system, and assuming that the system saturates for the whole input, تمام? So it's just gonna clip input. This one, if you clip everything and it's a saturated system, you will end up with square function. If you try to pick the information here from the amplitudes, you will end up with a constant signal. That's the AM case. The FM case, again, it's going to clip everything. But then when you try to extract the information, you are not really dependent on what happened to the amplitudes. You are trying to extract the information from here, from those frequencies, right? So you will end up with more or less, again, assuming that the clipping does not take everything to zero, you will end up with your information maintained. Well, this is one of the main advantages of frequency modulation versus amplitude modulation. Try yourself, for example, some radio channels here in Qatar are broadcast both in AM and FM. Try for the same radio channel to listen to the AM and go, for example, through the highway of Lusail, the one that goes through Lusail, south of Lusail, west of Lusail. That one goes under, like underpass and then up, and then underpass and then up in many places. You will see that the AM signal gets really bad when you go through small underpasses. If you use the FM, most of the time it's maintained. You will not have, of course, unless you go through a long tunnel. That's a different story. Tamam? Like in generally speaking, the FM signal is much more resilient to amplitude variations, whether they come from the channel or they come from the amplifier saturation. While AM is not resilient to that. It gets affected very quickly with amplitude variation. Any questions about this part? Discussion دي حد عنده تعليق عليها؟ لا. طيب, discussion كويس. Here is another effect, which is basically an extreme case in the case of compression, but we are not considering something from the same signal. We are considering the effect of an interferer in this case. So you have an interferer, which is at slightly different frequency from yours, and that interferer has a very high amplitude, and then you have your desired signal. What will happen, again, assuming that your system is nonlinear, okay, what will happen in terms of the received signal if we assume that the interferer is much larger? So the amplitude of the interferer is A2, the amplitude of the signal is A1. Taking the nonlinearity effect into consideration and focusing only on the components that will appear at the frequency of your fundamental frequency, because that's the one that you are going to filter out from the reception side, you will see that the amplitude of the interferer will appear as well as part of what you get in your own frequency. Assuming now that you are using amplitude modulation, so information lies in the amplitude, this is going to affect your signal somehow. So the interferer, even though it's not exactly at your frequency, but because of the nonlinearity, it will have some component leaking into your frequency. Okay? Now, if A2 is much larger than A1, then you can actually ignore this term, and you focus only on this one. So look at what you get, right? You get alpha 3 fine multiplied by A2 squared multiplied by A1. Now, if you try to decode this signal or demodulate this signal, alpha A2 is the dominant factor. So you end up with information which is looking from the interferer, which is even overwhelming your own information or your own signal. You don't know the interferer, so you cannot remove it from the expression, so you cannot really recover your signal.
Plus it can like saturate
your amplifier, right? So the end result is your signal is being blocked by the interferer. You cannot really recover it anymore by any methodology that you do at the receiver side, given the condition that the interferer is much larger than your amplitude. If it's not the case, then this would have been considered kind of a noise term or just an added small interference, and then when you decode, you recover most of your signal, right?
Is that how a signal jammer works?
It's kind of, but the jammer needs also to hit your frequency. Otherwise, you can overcome it by, لأنه طبعا receivers, they do overcome this effect. We're just talking about the effect. We didn't say how to overcome it, because there are ways to overcome this. When you design a jammer, you have to hit the frequency with very large amplitude as well. Yes?
So you get a signal with a higher amplitude that doesn't look as
That doesn't?
look as our original signal.
Yes, and you don't know it. It's just you are decoding something else. You are receiving or demodulating something that you don't care about. You want your signal, right? Yeah.
FM ما have
FM no. FM is a different story.
If A1 was dominant, I'll get A1 cube, not A1.
That's fine, because you will have A1 because of this constant term, and you will have A1 cube. That's fine, it's still your signal. If you are very keen, first of all, A1 is sufficient for you, right? And if you are very keen, you can also do some processing of that polynomial to recover your actual signal, because it's all your signal, right? Any questions here? So this effect is called desensitization, or in other terms, blocking. So the interferer is blocking your signal from being recoverable. Yes? Here is an example I want you to try on this one. It's very nice, has good concepts to it, because it combines a few of those things that we discussed. So a 900 megahertz GSM transmitter delivers a power of 1 watt to the antenna. So your transmitter is sending 1 watt to the output. Tamam? By how much must the second harmonic of that 900 megahertz user, so the fundamental of that user is at 900. But then because of nonlinearities in that system, it might also have a second harmonic. Tamam? How much this second harmonic needs to be suppressed, filtered out, attenuated, whatever the word you like, all of them, how much you need to reduce its amplitude, tamam? So that it does not desensitize another user at 1.8 gigahertz. And the second harmonic, its location is going to be at 1.8, tamam? And it will have a certain amplitude. How much you need to reduce that amplitude such that it does not desensitize a receiver at 1.8, and the guiding element here is that the 1 dB compression for that user at 1.8 is equal to minus 25 dBm. So generally speaking, you want your signal not to exceed that value, because exceeding that value means that it will push that system into compression and it will overwhelm the system. Tamam? So you need your received second harmonic not to exceed the minus 25 dBm. Tamam? Assume that the receiver is 1 meter away. Useless information. The more important one is that the 1.8 gigahertz signal is attenuated by 10 dB when it reaches the receiver. So that 1 meter will cause a 10 dB. That's the more important part. 10 dB drop in the signal. Yeah. Okay? How to solve that? Only how much should be, after reading all of this, tell me how much should be the reduction in the second harmonic of that 900 megahertz. As I said, best way to do this is to draw the problem. Here is my transmitter at 900 megahertz, تمام؟ ترسمه بلوك, ترسمه antenna, ترسمه أي حاجة, doesn't matter, تمام؟ And here is my receiver, which is at 1.8. My transmitter has a fundamental and has a harmonic. And now I'm focusing on the harmonic, how much it should be such that it reaches the second receiver at 1.8, and its value is going to be at or below the 1 dB compression of
how
that.
would I know what's like the second order harmonic, the actual like that power beginning before
اشتغل في المسألة. هتعرف. اشتغل في المسألة. انت you need to tell me how much it should be.
how much it should be,
Yes.
مش how much I need to decrease.
لا ما هي يعني you need to decrease it هنا معناها how much it should be. What's its value? How much its value should not be go above. تمام؟ try to solve it backward. يعني start from what you want to receive from that second harmonic and then reverse the effect of the drop in the channel. This will give you how much you need to transmit in the second harmonic. صح؟ Solve it backward. يعني solve it من الآخر للأول. From the end back. So if you start at the end, you want your received signal اللي هي ال second harmonic at 1.8 and the second user يعني. You want that one to be less than or equal to minus 25. Now, how much should that be such that after 10 dB drop, it's not more than minus 25? Exactly. Very simple. Very simple, yes. Yeah. Negative 15 dBm. خلاص? Yeah, so that's the solution. It's written here. Yes. So the solution says that the output power at 900 megahertz is equal to, that's first of all, just to see what's the fundamental power going out of there. And then you want to say later on, after you figure out the value of your harmonic, you want to say how much lower than the fundamental it should be. Tamam? That's a separate part here. But anyways, the output power of 1 watt is 30 dBm. عارفين تحسبوا 30 dBm is 1 watt. Take the log to the base 10. Sorry, divided by 1 milliwatt. وبعدين take the log to the base 10. So it becomes 30 dBm. 1 watt dBm scale is 30 dBm. Right? With an attenuation of 10 dB, the second harmonic must not exceed minus 15 at the transmitter, so that it is below the 1 dB اللي هو minus 25. صح؟ That means I want the received here to be minus 25 or less. تمام؟ And this received is 10 dB lower than the transmitted 1.8. If a transmitted 1.8 cannot be more than minus 15, so that when I take minus 10 out of it, it becomes minus 25. Right? So that's how you found the value of this one at the transmitter antenna, so that it's below that power. The second harmonic must remain at least 45. وهنا minus 15. Minus 15 from 30 is 45 drop. تمام? The first one is 30. Second one is specified to be at minus 15. What's the difference? 45. Minus 15 and 30 is 45 difference. And this means that the second harmonic must be 45 dBm smaller than the first harmonic, so that you make sure it's minus 15. لأن الفيرست أو الفاندامنتال سوري second harmonic وفاندامنتال first. So the difference here has to be 45 dB, such that you make sure that this is minus 15, because you know that this is 30 from the input of the problem. تمام؟ خلاص. نوقف على كده؟ نعم. جت منين؟ طيب. البروبلم بتقول لك ايه؟ It says that the 1 dB compression here تمام is equal to minus 25 dBm. تمام؟ وبعدين بتقول لك السيجنال دي اللي هي عند ال 1.8 when it's traveling this distance it's gonna lose 10 dB. تمام؟ يبقى السيجنال دي المفروض ما تزيدش عن كام such that it does not exceed minus 25 هنا. ما تنفع it cannot be more than minus 15 dBm. مظبوط؟ This is where we got the minus 15. طيب I got the minus 15. Now the compression او اللي هو سوري الفلترنج اوت ده is gonna be typically this harmonic in relation to the fundamental. فانا عايز اعرف الديفرنس between الهارمونيك والفاندامنتال المفروض يبقى كام. I know that this one is already 30 dBm and I know now that this one is minus 15. يبقى الديفرنس بينهم كام؟ 45 dB drop. تمام؟ ليه؟ Why do we care about this? Because when we filter out signals, what I'm getting from my transmitter probably is something that looks like this. تمام؟ الفيرست الفاندامنتال والفيرست هارمونيك. Now, if I'm doing a good design, after my amplifier, I might sometimes have a band pass filter to make sure I comply to the specs. الباند باس فلتر ده هيحاول يعمل حاجه زي كده. So it's going to drop this guy to a certain desired level عشان does not cause الانترفيرنس ده. ف I need to know how much my filter needs to drop the signal. drop الهارمونيك ده. تمام؟ That's why you need always to compute the relative relation دي. Okay? Any questions يا شباب؟
بس regarding the lecture notes and the recording.
حاضر.